Hello and welcome. Today I'm going to be talking about another problem from the FMWC Open. This one is feeding Excelopolis, which was a problem from round 2 of the competition a couple of weeks ago. This is an interesting one to talk about because I think the general reception was that this problem was maybe way too hard for the format, and it was kind of borne out in the scoring. I managed to get through this round with a score of 8 out of 1,000, and that was actually better than half of the people competing scored. I think the top score on the day was maybe 70 out of 1,000, and most people scored, 4, 6, 8, something like that. So this is going to be an interesting one to try to tackle quickly, but let's see how we can do. It's also going to be a good one to talk about design and how big a difference that can make, because I'll kind of show you what I came up with on the day, and then maybe show you, having had some time to think about it later, a better, more efficient way to do it. So let me just start with a bit of an introduction to the problem itself. So the idea is, you're a tribe of nomads, hunter-gatherers, and you've developed some agricultural technology, and you're settling down to form a city. And so you live in this grid of 7 by 7 cells, A to G, 1 to 7. So your city is going to be based here in D4, and then you're going to farm the area around that with your technology. And so this 7 by 7 grid, the numbers in it represent the fertility of each of the cells in those areas. So in other words, if you farm this cell, you'll grow 5 units a year. If you farm this cell, you'll grow 3 units a year. This one grows 2, this one grows 1, and so on. And so the idea is that you start off with 1 unit of population, so you can farm any one of these cells. So obviously you'll want to farm the most fertile one, and then after you build up a certain amount of store of food, you can get a second person in your population, go and farm the next most productive one, and then the next most, and so on. And the idea is you want to grow your population until you filled either the first square at round 1, or the second square at level 2, or the third square at level 3. And then there's a few other twists at level 4 and 5. Then the additional twist is the reason for these colors here, the blue and the green and the white, is basically the idea is you can't go too far from the center of your city until your population gets bigger. So in other words, the first up until you have a population of 7, you have to stay within zone 1. Up until you have a population of 17, you have to stay within zone 2. So for example, where I showed you, your first person goes to the 5 here, your second person can't go to the 5 there, even though it's more fertile, because you don't have a big enough population to go outside that zone. So they go to the 4 here, they go to the 3 here, and so on. But the twist is, so once you get up, so you've got a 5 and a 4 and then a bunch of 3s, but once you get up to 6, so your 7th person can go out into this second ring, but your other people can also relocate. So this person can go from a 3 to a 5, and this person can go from a 3 to a 5, and so your harvest can go up a chunk there. Again, one of the twists later on in the level 4 problems is that then you can't relocate, so you won't be able to farm all of these 5s right away. You'll have to build up to that. So that's the premise. I think I've covered everything. So let me show you what the kind of case file looks like. So basically the idea is you're given a single line all the way from A1 across to G7, which shows the fertility of the 7 by 7 grid around you. So for level 1, you've just got the innermost 3 by 3 grid populated. Then for level 2, you've got the innermost 5 by 5 grid populated, like that. And then for level 3 and on, you've got the whole 7 by 7 grid populated. And so the idea is basically at each of the first few levels you have to, so like for level 1, only the inner 9 exist, and the question is how quickly can you grow your population to 10. In other words, you've got 1 person on each of these, and then you grow to 1 more, and that's as much as you can grow because there's nowhere else for that 10th person to go. And similarly here, at the next level there's 25 cells, so the question is how quickly can you get your population to 26, and then at 49 cells the question is how quickly can you get your population to 50. And then, like I said, at level 4 the additional twist is that you can't relocate people, and then level 5 is a whole other thing, more complicated. If the video isn't turning out crazy long, then I'll have a go at that, but otherwise I won't. So let's hop to some calculations. The first thing I'm going to do is just take this grid of cells I'm going to copy, transpose that here. That's going to be the location. First thing I'm going to want to calculate is the zone, and the next, first thing I'm going to want to calculate is the fertility, and the next thing I'm going to want to calculate is the zone, because that's going to be important. So with a problem like this, you can either try to solve the whole case in a single row of the grid and then copy it down, which for simpler cases can work, or you can build a solution with a question selector and then use a data table to figure out all the different answers. So that's question 1. I'm going to pull in the data from here and so on down. So the fertility, I'm going to say first I'm going to use index to find the data. I'm going to match this against here. I guess I can just do it on the whole. No, do it on here. So match it against the whole thing here. Comma 0 for an exact match. And then where do I want to look up? I want to look in this whole grid all the way across. And I just want to make sure I've got the same. So 66 to 194, yes. And so I want the row to be that, and I want the column to be 0, meaning give me the entire column. And then I need to transpose that because I want it to be vertical. So transpose like that. And then hopefully I've got my fertility. That's not quite working. So B to BB, oh yeah, I've made it too wide. So it should go from column F. So probably at some point you might have seen I selected up there, and I probably selected up as far as a merged cell. And so even though I was looking from column F to column BB, that actually expanded my selection over as far as column B. So just fix that by making that column F. And then I should have, yes, it goes down to G7 like you'd expect. And the ones that are populated, let's just see, D3, D4, D5 should correspond to, D3, D4, D5. Should have, oh yeah, C3, C4, C5, D3, D4, D5, and E3. So that's the right ones populated, and then let's just check that it's, let's say, take one of the samples where there's all 50, and that seems to be working nicely. Okay, so the next thing is to work out the zone. So basically I want, zone 1 for those innermost cells, and then zone 2 for these, and so on out. So the way I'm going to think about this is the zone basically corresponds to how far you are from the city in the direction that you're furthest away. So in other words, here you're 2 cells horizontally and 0 cells vertically, so you're 2 cells away. Here you're 3 cells vertically and 2 cells horizontally, so it's about being 3 away. So I'm going to want to work out for each cell how far is it horizontally and how far is it vertically from the city. So let me show you that quickly. I'll just move this over so I can do so. Horizontal and vertical. So let's see, the horizontal is just the numbers, so that's a little bit easier. So it's going to be absolute value of the middle square, which is 4, minus the number of the column you're in, which is the right hand side of that. You could add comma 1, but actually I learned recently if you do right with no argument, it gives you just the rightmost one cell. So what are we saying here? We're saying we're in column 1, so the distance from column 4 is 3 units. And then if I copy that down, you'll see column 2 is 2 units away, column 3 is 1 unit away, column 4 is 0 units away horizontally. And it's the same idea vertically, except that obviously I don't have a number here. I've got a code. So you could do this by taking the left of that and then matching it against you could do a table of letters and match it against that to turn it into a number. Or the other thing you can do is you can use code to turn it into the ASCII code number. So A is 65, B is 66, C is 67. The main thing is that they tick up one by one, and so again I can just do minus code of the middle column, which is D, and that'll give me something that ranges from -3 all the way to +3, and then again I just put an absolute value around that, so that gives me my distance. And then having done that, the zone is just going to be the max of these two, with one exception. So let me just show you. Let's just say we want to check on this. So I'm going to say equals sequence, comma 7, and equals, actually, let me just do equals this. So let's just see what my zone numbers look like. So I'm going to say equals sumifs for my zone. Give me the zone where the location is the intersection of these two. So it's that and that. Copy it down and across. And then I'll just do a quick color scale highlighting. And so you can see it basically works except for the one exception, which is in the middle. So where it's 0 and 0 away, that's supposed to be part of zone 1, not 0. So easy fix for that. I'm just going to make the max of those 2 and 1. Copy that down, and now you see it's doing exactly what I want. 1 there, 2 there, 3 there, and in a kind of neat enough dynamic way. So now basically I've got a table that tells me, what's the fertility, what's the zone. So now what I want to figure out is, in each zone, how many units are there at each fertility. So here's what that's going to look like. I'm going to say zone 1, 2, 3 units by fertility. And I'm going to sequence 5, 5 minus 1. So count down from 5 to 1, and then I'm going to do count ifs. So what am I counting? I'm counting where the fertility is this. Oh, now, just a quick thing to watch out for, because it just tripped me up right here, and it often does. So if you have a dynamic array like this, where you're using, like in this case, C5 hash to reference it, if you select that range and then press F4 to lock it in, you'll see it's doing it for me now, but at the time I select it, so if I select this range and press F4, it doesn't actually lock it. It's not doing anything. So what I do is just delete that, then lock it in, and then put the hash back on. So I want to count where that is this, and where the zone is less than or equal to this. So in other words, in this case, when I'm in zone 1, there's 1, 5, there's 1, 4, 6 3s, and 1, 2. And that's actually the same as the example that I was showing you earlier. We're here. So there's 1, 5, 1, 4, a bunch of 3s, and then 1, 2. And then you go out to the next zone, you add 3 5s, and then a bunch of 3s, a bunch of 2s. So let's just go back over here. So by the time you go out to zone 2, you're up to 4 5s, still only 1 4, 13 3s, 7 2s, and then you go out to zone 3, there's no more 5s or 4s, more 3s, lots more 2s and 1s. So in other words, the fertility is getting lower as you get further away from the city, which makes sense. You want to place your city in the middle of the fertile zone. So now what I want to figure out is, for any given level of population, what is my harvest going to be? And I'll need to be able to do this for populations up to 50. Up to 49, because once you hit 50, then you're always done. So I'm going to say sequence 49 to fill that down. And what zone am I in? So let's just do a very quick lookup table. If we have at least 1, we're in zone 1. If we have at least 7, we're in zone 2. If we have at least 17, we're in zone 3. And then, still using VLOOKUP, ignore the haters. So 2, and just crucially leave out the last argument or put false, because I want an inexact match, a range lookup. And so that'll give me 1 up to 6, then it'll give me I'm in zone 2, then it'll give me I'm in zone 3, and so on down. And so now what I want to work out is, I'll explain why in a second. I'm just going to move this over by 1. I'm going to put this same countdown from 5 up here. And then what I want to figure out is how many units. So, here where I have a population of 1, I'll obviously just put it in the 1, 5. Where I have a population of, let me just change my freeze so that you can see those top few rows as well for now, and then I'll have to change it back later. So let's say if I have a population of 5, I'm going to want to put 1 here, and the other 3 here, because that's what I'm limited to at a population of 5. But then if I go down a bit at a population of 8, let's say now I'm free to use these ones, so I'll want to put 4 here, 1 here, and the other 3 here. So the idea is basically, in whatever zone you're in, you fill up the 5s as much as you can, then you flow down and fill up the 4s as much as you can, flow down and fill up the 3s as much as you can. So let me show you a little doodle that might make this clearer. So here's the idea. You've got, as your population goes up, basically you're filling up the 5s until there's no more 5s left. You're filling up the 4s until there's no more 4s left. You're filling up the 3s until there's no more 3s left. Filling up the 2s and so on. So what does the graph look like for, let's say zone C, which is in green? It looks like nothing at all until you've got enough population that you've filled up zones 1 and 2. Then it climbs with the population, and then it levels off once you've filled up that zone. And so one neat way, so this is like a realistic thing that comes up a lot where, like I was just looking at a problem the other day where it's customer acquisition costs. This is your cheapest channel and you can acquire, so many customers through that. This is your second cheapest channel and you can acquire so many customers through that. And so you want to fill up, each channel in order of like lowest cost. So what does this function look like? Well, if you think about it, it's never below, it's never below 0. It's never above the total capacity of that band, and then it goes up with the population. So the way that you can do this is just a median of these 3 numbers. So you've got one thing that goes up with the population so that it hits this right at the start of that. You've got one thing that's flat at 0 and one thing that's flat at the population. I don't know if that explanation helped at all. It helps in my head, but let me just show you the formula now, and maybe it'll make it more clear. So it's the median of 0, and then your cap, which depends on your zone. So I'm going to index these 3, and the zone is going to be my count. So I'm saying, if I'm in zone 1, then my cap is 1. If I'm in zone 2, it's 4. If I'm in zone 3, it's 4. And I'm not locking in the column, so that'll move as I go across. And then the population that I have available to put in here is the total population minus, lock in the column, not the row, minus any population I've already allocated. And that's why I copied this over, so I'd have an empty column here, so that I can start my sum from there, because what that means is basically I can use the same formula for the 5, 4, 3, 2, and 1 all the way across. So in other words, this sum will always be 0, because this is just an empty column, but because I have this empty column here, I can lock my sum on there, and then, when I get further over, it'll point to all the rows that I've already allocated. So that's the formula, and let's just see if it's working. I copy across. That is not quite working. Why is it not working? Let's see. So I'm just going into the formula auditing. So I index on there. Oh, wait, what? Yes, that'll give me 1, fine. So my population is 1. I subtract off the sum of the ones I've already done, and that's 0. So why on earth is that giving me 1? Oh dear. Oh, sorry. Okay. Yeah, I see what's wrong. It's this. So this is locked on the row instead of the column. So that should be $J, so that it stays pointing to the zone column when I copy it across, not the other way around. Okay, so now, good, I've got 1. So then when I add 1 more, it goes into the 4. Now I've filled up my 5s and 4s, so everything else should go into the 3s for a while, which it does, all the way down to a population of 6. And then I should see a bunch of people relocating up to 5, which I do. So now I've got 4 people here, 1 person here, and 2 there. And then I should see everybody continuing to, sorry, I'm not coming back down here, here we are. I should see everybody continuing to fill into the 2s until that gets full, which will be at 13. Now, if there were more 4s and 5s freed up when you got to level 3, then you'd expect to see relocation, but actually in this case there aren't. So this will just keep ticking up, up until we fill up all of the 2s. And then you can see here we've started filling up the filled up all the 3s, so now we're filling up the 2s. And then in the end, when you copy it all the way down, you fill up all the way down to everything. So that's the idea there. I'm going to fix this freeze now so that I'm back to just having a more reasonable number locked, because I do have a very small screen here. So that's that. So with a population of 1, I have 1 5 with a population of 2, I have a 5 and a 4, and so on. And so that makes it easy now for me to say, what's my harvest with this population? And it's just sum product of this with this. And again, I have to delete the hash before I press F4 and then put the hash back. So here I have a harvest of 5, then a harvest of 9, then a harvest of 12, and so on down. And when I'm harvesting everything, it's 123, which hopefully will match back to the sum of the fertilities, and it does. So that's a good little sense check. So then that's my harvest, my surplus. Oh, maybe I forgot to mention this earlier when I was describing it. So the idea is you harvest 1 to 5 units, each person eats 2 units. So your surplus is your harvest minus 2 times where population is back over here. So harvest minus 2 times population equals surplus. I'm actually going to redo my freeze just to start from this row now, because this is kind of where it's all happening now. So freeze there. So that's my surplus. I copy it down. Then let's just talk about the starting amount in the store or the warehouse. So obviously for the first turn that starts off at 0. I'll just color that differently, and then each subsequent turn it'll be something different. And the question is, how many years do we have to do like this before we get to the threshold to grow? So the idea is that once your accumulated surplus is at least 10 times the population, then you're able to add 1 more person to the population, and you throw away or trade or harvest. I don't know what exactly the logic is for, but you get rid of the 10 times the population. So in other words, in this case, you're accumulating a surplus of 3 each year, and you have to get above 10. So the simplest thing is to say 10 times the population. That's the number you need to get to is 10, minus whatever you start with in the store, which in this case is 0. So you need to accumulate 10, and you're accumulating at a rate of 3. So it's going to take you 3.33333 years, but we're told the harvests only happen at the end of the year, so I'm going to have to round that up to a whole number. So round up, comma 0 gives you a whole number. So it's going to take 4 years to get to there. And so then my starting store for the next year is going to be the initial starting store 0 plus 4 years of a surplus of 3 minus, so whenever you grow your population, you get rid of 10 times the old population. So in other words, I harvest for 4 years, I get up to a warehouse storage of 12, then I throw away 10, which is 10 times my 1 population, I'm left with 2. And now I'm harvesting at a rate of 5. I have to get to 20, which is 10 times my new population of 2. So that's going to take me another 4 years, and that'll get me to 22. So again, I should be starting with 2. That's right. And now I need to get to 30. I've got a surplus of 6 per year. So you can see the surplus relative to the population is going down because you're having to harvest less efficient land. So let's see, that should take me 5 years. And then I've got 5 by 6 is 30, so I'll still have 2 left over, and so on. So I'll just copy this down. That's taking its sweet time. Oh no, I must have triggered it too. So I've got another file open with a version of this I worked on before that I might show you later, but that's got some tables in it. I had turned on tables without calculations without tables, but for some reason it looks like I've triggered the table calculation. So now it's running super slowly. That's a little disappointing. Or else it's crashed. I can't quite tell. Oh, there we go. No, don't start calculating everything again. What are you doing? I seem to have made it really mad for some reason. I don't know why. That's no fun. Okay, there we go. I think. Okay, so that's how it works. So now let's see if it is actually working. So let's see, which I'm currently on. I'm going to unfreeze my panes now, go back up here. I'm on sample 3. And so sample 3, I'm working out how long it takes me to get to 50, and if I've got the answer right, it should be 448 years. So let's see. To get to 50, it's very simple. I just sum up how long it takes to add the 2nd, the 3rd, the 4th, the 5th, up to the 49th, and it's 448. So I feel pretty good about that. And then let's just see, do I work out on the lower numbers? So on sample 2, I should take 184 years to get to 26. So sample 2. And this time I only want to get to a population of 20. So yeah, first 25 years, because I'm adding 25 units to the population. That's 184, good. And then last quick check, if I've got those two right, it'd be pretty weird to get the last one wrong, but let's try sample 1. And so you can see there's, with you know, the answer to how long would it take you to get to a population of 26 when there's only 9 units available is typically negative, because if you had a population, so here the sum of all of these is 29, so if you have a population of more than 15, then you're consuming more than you're harvesting. So you know, this how many years would it take calculation turns negative, but that's okay, because in this case I'm only interested in summing the first 9 years, and that gives me 54, just like I'm expecting. So I'll just put that in the cell. 9 rows gives me 54. Okay, so that feels pretty good. Feels like that's working. I haven't been keeping track of my time, but I think I'm doing okay versus the sort of half an hour. I'll very quickly show you, if you you know, if you want to actually kind of fill in the answers here, how do you do that? Well, you could, you know, select the cases one at a time, and then, whoops, and then go and look at each answer. Or you can do a data table. So let's say sequence, is it 30 questions in the first one? No, 15 questions in the first one. So basically a data table is telling Excel, take each of these 15 values 1 to 15 and put it in this cell. I'll tell it which cell, and then tell me what this number here, which is the sum of the first 9 years, would be. So we'll go DT, column input cell is going to be this one, the question selector. Then I'll tell that to calculate. It's going to calculate my data tables in the other tabs as well, but hopefully it won't take too long. That spins for a second and then gives me all the different answers. And if I've got the version of the workbook with the answers here, so let me just check against that. I'll just copy these over, value paste, and yeah, they all check out, so that's good. And in the same way, you could you know, basically just do the formula summing the first 25 years and data table that for 16 to 30 and so on. So that's how you do levels 1 to 3. Let's talk about level 4. So in level 4, basically this reallocation that we're doing here does not work anymore. So let's go back to sample 3, because that's the one that we were looking at before. So it'll look a little bit more familiar. So in this case, you know, we do 1, then 1 goes into 4, and these go all the way down to 3, and then as soon as we get to 7 population, we reallocate a bunch of people, move up to 5. So in this version, we're not able to do that. So let's just take this. Yeah, let's just build another version of it. So we'll point back to here again. Hash, and so for the first row, it's going to be exactly the same. And actually, you could even copy that down to the first 6 rows, but it'll work the same. So then for row 7, what are we going to want to do? Well, I think what I'll want to do is basically work out what's the best next move. And what is best next move going to be? I'm basically going to compare this distribution to the best distribution possible at the next level and see where the first gap I have is. So in other words, if my number of 5s is less than 4 and I'm on level 2, then I'll want to do a 5 first. If I've got 4 there and 1 there and 13 there and this is less than 7, then I'll want to put 1 and a 2. So what would that look like? I'm going to say max of if this is less than index. So I'm going to take one of these rows, depending on which zone I'll have access to. So index that and lock that in. The row I'm going to want to take is the zone, but it's the zone I'll have access to in the next layer. So in other words, you know, if I'm on If I'm on 6, then in the next layer I'll have access to 7, so I'll want to think about that. That's the row, and then the column is 0, meaning give me all the columns. So if that's less than that, then I want this number. And again, I'll lock that in and then add the hash back. Otherwise, that. So my next best move here is a 4. So now I'm going to say equals this plus this equals this. And then you can see that adds a 4 there. And then it tells me my next best move is to add a 3. And so right now, I haven't got access to any new zones, so this matches exactly the distribution that I had before. But now, you can see this is the row where I reach, here, where I reach a population of 7. So now I'm adding 1 to 5, and then again I'll add 1 to 5, 1 to 5, until now I've filled up my 4 available 5s. I've already filled up my 1 available 4, so now I'm back to filling in 3s. And again, we kind of talked about this earlier, that in this case there's no more 4s or 5s available in the outermost zone, so then it'll just follow the same pattern the rest of the way down. So I'll just go down to 50, and then I guess I'll just copy all the rest of this over. I think that'll work, but I'll have to check them all quickly. So, oops. So my harvest now is going to be based on those, and it's already locked to that one, so that's fine. And again, I've still got 123 at the end, so that's good. Surplus is going to be harvest minus 2 times, and I didn't lock in the column, so I'll have to go back over here and find the population. It's that one. I suppose I could lock in the column this time. Fill that down. Starting in 0 years. So I'm going to, again, sorry, got to do the population as column I, not column U. Should have locked that in before, but fine. So it's 10 times the population minus your starting thing divided by your surplus. That's right, that's still good. And then this, again, 10 times the population. I just got to change it to refer to column I. And then I just copy the rest of the stuff down. And then copy down. And so I think that's the only thing I have to change. So let's just see. If I go sample 4, I'm looking for an answer of 450. So let's see if I making a video. Hi. So let's see. It should take me 450 years according to this, and it does. Cool. So that's that one working as well. All right. So that was my wife appearing in the bedroom, wondering why I'm making Excel videos and not going to bed. So I think that's my sign that I don't have enough time to work on level 5 today. So instead, what I'm going to do is I'll do a sneaky. Here's one I made earlier, and give you a quick tour of how I did it. It is, compared to the sort of relatively clean logic for this one, it is definitely way more complicated. But, well, anyway, I'll just show it to you. I don't know. I was hoping to kind of time this so that I could see if you could actually make this within an hour, within half an hour. I suspect the answer is probably not quite, or maybe if you had a super clear sense of the design in your head right from the start. I don't know why it is not letting me close that one down. Let's save. Okay. Close the rest of these down, I guess. Okay, so here is my setup for level 5. So the idea in level 5, just to quickly show you, is you have fertility degradation. So if you farm the same cell for 10 consecutive years, fertility lowers by 1 unit. So in other words, back to this situation, if I farm this cell for 10 consecutive years, now it goes down to a 4. If I farm it for another 10 without stopping, it goes down to a 3, and so So basically means that you're going to have to kind of dynamically update this grid as you go along. And then as soon as you don't farm it for a year, it springs back up to where it was. And then it clarifies, if you have several cells with similar fertility, but not enough people to work on all of them, you should leave alone the ones that will refresh to higher amounts. So in other words, if you have a 5 cell that you've farmed for 20 years and it's come down to a 3, and you have a 4 cell that you've farmed for 10 years and it's come down to a 3, and you have a 3 cell that you haven't farmed for 10 years and it's a 3, then you should leave the 5 one alone, because that's going to spring back up to a 5, versus if you left the 4 or the 3 alone, the 4 would go back up to a 4, the 3 would stay where it is. So you get the most benefit by neglecting the one that'll spring back up the most. So here's the layout. Obviously somewhat similar logic in that you've got, your population, what's your maximum zone, what's your harvest, what's your surplus, what does that do to the store, except that this time it's laid out by year instead of by sort of generation, as the previous one was. And the reason for that is obviously the fertility changes year by year, so you have to do that. So what is the logic? So basically I've got 3 blocks. I've hidden most of the cells, but each one of these is from A1 up to G7, A1 up to G7, A1 up to G7. So I've got 3 blocks. One of them is the fertility plus a tiebreaker for a given year. So let me just... so yeah, the way the logic is set up, the fertility is zeroed out if it's not in a zone you can reach. So that's why these are showing blank for a while, but then eventually you get down to here. So this has a fertility of 2, of 2, of 2, and so on. Then you get a flag for usage. So that's basically saying, are you using this cell? So you'll start off using one of the most productive ones, and then eventually when you grow you'll add another one, and so on. And then you've got another one here keeping track of cumulative years. So in other words, I've used this cell for 1 year, 2 years, 3 years, 5 years, up to 10, up to 20. And then you can kind of see, when this one gets to 10, you leave it alone for a year. When this one gets to 20, you leave it alone for a year. So that's kind of how the logic is working there. So let me just quickly show you what the formulas look like for each of these. So year is just a sequence. The question in this one asks you what happens at the end of 500 years. So we're just going down to 500. Population starts off at 1, and then I've got a logic thing here to say, am I big enough to grow? In other words, is my store 10 times my population? And if it is, then the population the next year adds 1 based on that. My maximum zone, again, just a lookup, 1 or above gets you to 1, 7 or above gets you to 2, 17 or above gets you to 3. Minimum fertility, that's basically looking at the minimum of this. So the reason these numbers are weird, like it's not just 5, it's 5.002003, is because I've got some tiebreakers going on here. I'll explain that in a minute. But so this is the lowest fertility that you'll harvest. This is what is your harvest. So you're taking, the fertility times the 1 flag that says, which ones are you harvesting. So take the product of those, and then int is to get rid of all this 002003 after the decimal place tiebreaker stuff. So that tells you your harvest. Then the surplus again is just harvest minus 2 times population. The store at the end. So obviously for the first generation, it's just whatever your surplus is. And then it's the previous store plus what you added to the surplus minus, if you grew the population, 10 times the old population. So here again, same logic at the start. You harvest 3, 6, 9, 12. Once you've got 12, you're ready to grow. So then you take away 10 times that, so you get down to 2, and the next year you have a surplus of 5, so you add that to 2 and you get up to 7, and so on down. And then this grow is just saying if your store is greater than or equal to 10 times the population, you're ready to grow. So so here I've got, this is the most complicated part. This is the kind of the part that's doing all the heavy lifting. I'm going to come back to that last. But basically the idea is this is the fertility plus various tiebreakers. So in other words, I've got a tiebreaker to say that I would prefer to harvest something that will, jump up more if it's degraded. I've got a tiebreaker to say that I'd prefer to harvest something if it's, I'd prefer to leave something unharvested if it's close to degrading, that kind of thing. So I'll come back to that logic in a minute. And then over here, I'm just saying if I ate, so in other words, if the fertility is blank, and it's blanked out if the zone you're in is less than or equal to your max zone. So in other words, here your population is small, so you can only do zone 1. This is in zone 3, so it's blanked out. So if it's blanked out, then 0. Otherwise, if the fertility is 0, so in other words, if the int of this fertility number is 0, then I don't put any person there. Otherwise, I've got just this minus minus, which gives me 1 if the fertility is greater than or equal to the lowest fertility that I'll harvest. And this min fertility is just the nth largest of these fertility plus tiebreaker numbers, where n is your population. So in other words, with a population of 1, I just take the biggest one. With a population of 2, I take the second biggest one, and so on. And then this cumulative years is just, if you're harvesting this year, then give me the previous number plus 1. So let's just take a quick look at that in action again. So, I start off harvesting this one. So then, I'm harvesting it again, so I add 1, I'm harvesting it again, so I add 1, so on down. So, this starts off as a 5, after 10 years it drops to a 4, I've got another 4 over here, then this one drops down to a 3, so I stop harvesting that and go over and harvest a different 3 somewhere over here. And then, after 20 years, this one drops down to a 3, and then at that point I'd prefer to harvest some other 3 and let that go back up to a 5, and so on. So that's the logic there. So, like I said, this is the section that's kind of doing all the work. So the logic is, I want to say, obviously 5 is the highest fertility I can have, so I prefer 5s over 4s over 3s over 2s, but then I want various different, so this is pointing up to the top to the initial fertility. This is pointing over here to, so int of that over 10 is, in other words, if this is less than 10, if it's 0 to 9, then divided by 10, you get a number between 0 and less than 1, so the int of that is 0. So in other words, no degradation for up to 9 consecutive years of harvesting. As soon as you hit 10, that becomes a 1, so you're subtracting 1. As soon as you hit 20, it becomes a 2. As soon as you hit 30, it becomes a 3, and so on. So this minus this is your fertility after the degradation. And then I've got various other tiebreakers down here at lower preferences. So here I'm saying 6 minus the initial fertility. So in other words, the higher the initial fertility, the less I want to harvest this one compared to other ones that have the same fertility now. So in other words, if I've got a whole bunch of ones that have a fertility of 3 now, the ones that had an original fertility of 5 before they degraded are the ones that I want to harvest least. And so that's why it's kind of 6 minus. So in other words, this will be, this will be a 1 for something that started off at a 5. It'll be a 2 for something that started off at a 4, 3 for something that started off at a 3, and so on down. So it's a higher number for a higher number for lower original fertility, because that's what I want to harvest first. And then this, the divided by 500 is just because this is a number that's up to 5, so I divide it by 500, I'll get something that's between 1 500th and 1 100th. And so the logic there of dividing by the 500 is I want to make sure that I never get my harvest count off because of having these fertility, so because of having these tiebreakers. So in other words, the most of these tiebreakers I'll ever add up is 50, so I'm dividing by 5 because that's the biggest they can be, and then by another 100 to make sure that the sum of all of these tiebreakers never makes me think that I'm harvesting more than I am. Then I'm subtracting something for the accumulated degradation. So in other words, if I've got multiple different ones where it's the same current fertility and it's the same original fertility, then the one that I'd prefer to harvest is the one that I'd prefer to harvest is the one that's furthest away from degrading more. So in other words, if I have 2 5s and I've been farming one of them for 6 consecutive years and one of them for 1 consecutive year, it would be better to stop farming the one that's at 6 years and reset the counter on that, because then I'll be 10 years away from degrading on that one. So that's that extra tiebreaker. And then the last tiebreaker is and again, that's divided by 25,000. The idea there is, it'll the degradation will never be more than 50, because after 50 years, any fertility will go down to 0, and you definitely won't harvest it the next time. So I want to make sure that this is smaller. So the smallest this can ever be is 1/500. The biggest this can ever be is 49/25,000. So that's basically a way of saying this always has to be smaller than this, because that's the way I want it. I want it first to be on fertility, then to be on original fertility, then to be on accumulated degradation, and then the last tiebreaker is just the column number and divided by a really big number, 10 to the 7, to make sure that, again, that never gets any bigger than this. And so the idea is, with the column number as a tiebreaker, there's never two that are the same. So what I'm going to end up with is 50 different numbers, and that's why this thing here is saying give me the largest, or the 10th largest, or the 47th largest, will always return kind of one unique number, and then this thing saying, am I greater than or equal to that, will always give you ones just for exactly the right number. So in other words, the sum of these 49 things will never be different from the population. So that ended up being a little complicated, but hopefully you were able to follow along. Obviously, it's level 5 for a reason. It's crazy hard. If you were able to get that done in half an hour, I'd be very impressed. Like I said, even having kind of designed and built this, I'm not sure that in the time I had left over after building the first 4 that I could even rebuild this, not to mention coming up with a design on the day. But the last level is designed to be hard, so that's okay. So I know I said at the end of the last one that I was going to try and make this a regular thing, and then I promptly didn't post again for more than 2 weeks. Sorry about that, been busy at work. But hopefully things are quieting off again now, so I am going to go back and double down on my original claim that I am going to start making more videos now, hopefully. We'll see how the Christmas holidays go. Yeah, I think that's all I've got. I'll see you next time. Thanks.